But it's back now. All right. So here we go. This is chapter 13. If you look over there at unit 7, it's the largest unit remaining. So this unit is key. And unit 8 isn't that long. It's just a little harder, a little more thinking. Unit 9 is easy. Unit 9 is easy. So, like I said on here, this is chapter 13 in the book. Chapter 13 in the book, which is equilibrium. We've been hitting at this, how this is the foundation for everything rest of AP Chem. So, here we go. Many chemical reactions are reversible. Many chemical reactions are reversible. And in terms of chemistry, you may see on the AP test, examples could include a solid. A solid dissolves. How can you get a solid back? It would have to do what? But what would the solid do? Recrystallize. You were close. Then recrystallizing. I mean, kind of. Electrons being lost and gained. Electrons being lost and gained in redox reactions. You guys remember redox? Leo the lion goes grr. We'll get back. Oil rig. We'll get back to that. The last chapter. And H plus ions being exchanged in acid-base reactions. In acid-base reactions. Most of these reactions come with some kind of observable event. Some kind of observable event. So, a color change, a flash of light, heat. Well, I guess you can't observe heat. You can feel it. Yeah, I guess it's observable. Bubbles. That will allow you to see that the process is reversible. So, a dynamic equilibrium. I don't know why we have to put dynamic in front of this because it just sounds fancier. A dynamic equilibrium exists when the rate of the forward reaction is equal to the rate of the reverse or backward. Either one is fine. Yes, you were very close that time. At the beginning of a reaction, of a reversible reaction, the reactants are going to be the reactant concentrations are going to be what? At the beginning?
Low.
High. They're going to be high because they're my reactants. And as a result, the forward reaction is also going to be high. Because I have a lot of ingredients, right? I have a lot of ingredients. It'd be the opposite for products. Because I basically, unless I tell you so, you start out with how much products? Nothing, right? You start out with nothing. Baking a cake's not a great example, but you mix your stuff together, right? As it cooks, you get more cake and less batter. Yes?
Yeah.
Not a very good example because that's not reversible. But anyways. Well, I mean, I guess when you digest it. Now I just want cake. It's been 18 days. It's been 18 days. I literally ate cake 18 days ago. All right, we gotta get, that's my bad. All right, here we go. As the reaction proceeds, the reactant concentrations keep falling and the forward rate of reaction will decrease. Once again, it's the same but opposite for the products. Do you guys remember this graph I showed you last chapter? Yes? Yes? Reactants go down, products go up. Okay, well, I showed it to you. Remember how we had like NO2 and like, it's fine. It's fine. It's the end of the year. All right, I appreciate your honesty. After equilibrium is reached, a sudden intro in reactants, that doesn't look good, I should write the whole word, a sudden introduction in reactants would result in a dramatic increase in the what rate? Which way? Forward. So, yes, if I add more reactants, it's going to keep moving forward. Then a new equilibrium would eventually be reached. It would go back to equilibrium again. You're going to get to see that in lab next Thursday. One of those. Next Wednesday or Thursday. Flip the page. We're going to get all the notes out of the way first. Just not today. I'm saying over the next probably 3-ish days. Notes marathon. It starts. Because tomorrow we have short periods, right? Yeah, bring snacks. If you guys want to bring snacks next couple days, go for it. Friday would be good for snacks. Monday would be good for snacks. Bring lots of cookies that I can't eat. So I'll just drool over them while you guys are eating.
Why can't you eat?
Because I'm not drinking pop or eating dessert or candy until I go to Disney World. Also, huh?
You're gonna get like super sick.
No, I won't. Also, you guys remember how I ate that like week and a half old? What did I eat? The turkey. Code green, by the way. That worked out fine. All right, that worked out fine. Yeah, that worked out fine.
I was also the Tic Tacs too.
The 7. How old are those Tic Tacs? Where are they? I only eat one a year. July 2011.
Wow.
So 13. Did I eat that in this period this year?
Yeah.
What an honor. What an honor. Because I only eat one a year. So next year.
They keep that flavor?
Yeah, it tastes good. I also, you know what else I read? We're going down this track. Let's keep going down. I saw someone on social media yesterday, a can of Spam. That was from 1960. Somebody, I think, it actually might have been in my AP classroom. My AP chemistry teachers, I don't remember. Anyways, we're a bunch of nerds. Okay, we're just all nerds. This Spam was 60 years old, and it was completely fine. But if you think about Spam, it's just like preservatives in there. So if you're trying to build a bunker, buy Spam. Buy Spam. Who here has ever eaten Spam? It's good. Do you fry it? Yes. Yes. Fried Spam is, it's amazing. I got a can in my stocking this year from Santa. So I might have to have.
Yeah, my grandma's a really big fan.
Yeah.
We cook it up every time.
I'm having omelets tonight. That would be good. Spam omelets. Yeah. Omelets. All right, we got to keep going. We're going to keep going. When equilibrium is reached, it may appear on a macroscopic scale. Macro means what? So like to the naked eye, that the reaction has what?
Occurred.
Stopped. That the reaction has stopped. But on closer inspection on the microscopic scale, it would confirm that it's still going. It's still going. So at equilibrium, both products and reactants are present in the mixture. If the products and reactants have observable differences like color, the reaction mixture should be a combination of the two. For example, I have a reaction where my reactants are red and my products are blue. If this reaction is at equilibrium, what color should it look? It would look purple.
This is getting dangerously close to biology.
It won't get much closer. All right, it won't get much closer. So, it should look purple if it's at equilibrium. Depending on the amounts of reactants or products, that will change the color, and you could estimate the relative numbers of reactants or products in the mixture. So if it's looking dark red, you have more what?
Reactant.
Yeah, you got it. You have more? Yes, you got more. Yes, you got it. So, great job. So, now, for the most important K left in chemistry, and there's more to come, all right? This is the equilibrium constant. This is the equilibrium constant. So put a star by this. The equilibrium constant, sometimes seen as Kc, right? So it's kind of repetitive because it's Kc, is given, here's the key, at a constant temperature. Put a star by that. Constant temperature. The temperature cannot change. So, consider the equilibrium below, where little a, little b, little c, little d are the stoichiometric coefficients. Of substances capital A, capital B, capital C, capital D, respectively. So we're going to write an equation. So we're going to have little a, big A, and these are all going to be aqueous, plus little b, big B, aqueous, is in equilibrium with little c, big C, AQ, plus little d, big D, AQ. So there's my equation. So the lowercase letters are my coefficients. The uppercase letters are my chemicals. The way you write a K expression is always two things. Number one, products over reactants. It's always products over reactants. Number two, the coefficients become the exponents. The coefficients become the exponents. I guarantee you on the AP test, you will have to write a K expression. And it's easy. It's easy. So the K expression for this would be big C, concentration of big C to the little c, times concentration of big D to the little d, over concentration of big A to the little a, times the concentration of big B to the little b. That is the K expression, the equilibrium expression for this pretend reaction. So, products over reactants. Did you guys see what I just did there? Yes. Okay. So this is where concentration represents equilibrium concentrations, also known as the product, which you guys can see, of the equilibrium concentration of products. It's the product of the products. We're multiplying. Raised to their stoichiometric powers, divided by the product of the equilibrium concentrations of reactants, raised to their stoichiometric powers. You guys are going to like this next two lines. K has no units. There are no units on K. Coulomb's law. Hydrogen bonding. All right? Because why? They cancel out. Right? The units are going to cancel out. So you never have units on K. I know. It's kind of nice. Yes. So, a couple side notes. Side note number one. KC expressions. So KC expressions don't include pure solids. So you can put lowercase s in parentheses. Or pure liquids, which would be what? Lowercase l. They don't include pure solids or pure liquids. Now, most of the time, what is your pure liquid going to be? Water. Now, the example I'm going to give you is going to be water AQ coming up, but just pretend like it's it. Okay. Just most of the time, if you see H2O liquid, it's not part of it, or a solid, not part of it, because that's not going to change the equilibrium. Not going to change the equilibrium. So you have to have one of two things. Then you have to have a solution or a gas. And for a gas, you do KP, equilibrium pressure. Right? I know. Mind blown. Side note number two. For number two, using KC at equilibrium gives you K. If you use your equilibrium expression at equilibrium, you get K, comma. But at other points, specifically, most of the time, parentheses, the beginning, if you do this expression at the beginning, you get Q. Q is called the reaction quotient. Other points, beginning, you get Q, which is the reaction quotient. So Q, it's the same equation. Same equation, except for they might say you have these starting concentrations, right? So if they give you starting concentrations, you find Q, right? And then you're going to see, we're going to compare Q to K, And that's how we'll know if the equation's moving forward, if it's moving backward, or if it's in equilibrium. I know. I was at Michael's last night, and they have a bunch of Super Mario fabric in their like fabric section. Just thought I'd let you guys know. What's that? We will be able to tell. I'll show you. We're not there yet. We will be able to tell them. So an example, decomposition of hydrogen peroxide, write the expression for Kc. Do you guys remember doing this freshman year and also in CP Chem? H2O2, AQ, breaks up into H2O, AQ plus O2, AQ. Remember how we put the hydrogen peroxide in? We put yeast. We lit the stick on fire. We blew it out. We put it down in, and then it relit because of the oxygen gas. You guys remember that?
Yeah.
Okay. We did that. Is this balanced? No. So there'd be a 2 here, 2 there. So if I needed to write the K expression for this, I would say the following. I would say Kc is equal to concentration of H2O to the second times the concentration of O2 over, you don't have to write it because we know it's first, but it is first. You don't have to write the 1. The concentration of H2O2 to the second. So, 2 things people mess up on this. First of all, they don't do products over reactants. Second of all, they forget the coefficients. You will have to do this on the AP test, I guarantee you. Easy point. Easy point. It's one of those basic things that you just have to know how to do. Cannot turn my page. Okay, flip the page. All right, so calculations where equilibrium has already been established. Consider the following, where butanoic acid, so that's Ba, reacts with ethanol. This is ethanol. I'm just making a note. That's going to help us later. To produce the ester ethyl butanoate, that's Eb, plus water. In 3 separate experiments, all at the same temperature, equilibrium was achieved, and then the following data were collected. In each experiment, calculate the equilibrium constant and comment on the values. So, I need to write a K expression. So, Kc is going to equal concentration of C3H7CO2 C2H5 times the concentration of H2O over my reactants, concentration of C3H7CO2H times the concentration of C2H5OH. So there's my K expression. Now, I'm going to pick a trial. I'm going to pick trial 1. So for trial 1, Kc is going to equal moles of ethyl butanoate. The first thing is how many? 20 moles. Times moles of water, which is 20 moles. Divided by moles of butanoic acid, which is 10 moles, which is in trial 1, times moles of ethanol, which is also 10 moles. Is everybody okay? What is going on here? What I've done so far? Yes? I wrote the K expression, I subbed in numbers from trial 1.
So there's no exponent.
Well, they're all 1, 1, 1, 1. So no exponents. There have to be coefficients for there to be exponents, right?
Yep.
Okay. 20 times 20 is 400. 10 times 10 is 400 divided by 100 is 4. So we're saying that K equals 4. Kc equals 4 for trial 1. Let's look at trial 2. Let's not even write it out. Trial 2. 10 times 40 is 400. 5 times 20 is 100. 400 divided by 100 is 4. Last one. 10 times 12 is 120. 30 times 1 is 30. 120 divided by 30 is 4. So this proves these are all the same. They're all the same. We already knew they're at equilibrium, right? It said consider, but why are they all the same?
They're the same formula.
Right here.
Oh, same temperature.
They're the same because temperature is constant. If the temperature stays the same, your K value cannot change. So eventually, there's going to be some kind of question that's like, if this changes and this and this and this and this and this, all changes at 40 degrees Celsius, what happens to K? Same. Yes?
So, is temperature the only thing that can change it?
It's not the only thing.
Okay.
But if temperature is constant, it's not going to change.
Okay.
So we're going to get into all that probably tomorrow. What else can change it? All right, here we go. Calculations where initial amounts are known. Then equilibrium is established. This is where we use ICE tables. An ICE table is a classic calculation that you'll be doing now until you're done with chemistry. All right? Whenever that is in college, or maybe that's just this year. But ICE tables are key. So I'm going to show you how to use it. Number 2, using the reaction. In the case he calculated in question 1, which was 4, right? Calculate the number of moles of each substance present at equilibrium when 1 mole of butanoic acid and 2 moles of ethanol are mixed at the same temperature. So, before we do this, in any equilibrium, the reaction is incomplete. The reaction is incomplete, meaning we can't predict the number of moles of products purely based on the stoichiometric like we have been, right? Because everything we've done so far are reactions that go to what? We assume that all the reactions went to what?
0.
Completion. They all went to completion. In order to account for this, we have to use an ICE table. Notice I'm putting ICE in all caps. So first thing we're going to do is we are going to, I know, very interesting. We're going to write our equation out. So our equation is still C3H7CO2H gas plus C2H5OH gas is in equilibrium with C3H7CO2 C2H5 gas plus H2O gas. Here's my equation. So to set up an ICE table, over here on the left, I'm going to have I. I stands for initial. I'm going to have C. Any guesses of what C stands for? Change. And you guys should all know what E is.
Energy.
Equilibrium. The big buzzword of the day.
I really should.
E is equilibrium. So, my initial of C3H7CO2, they said 1 mole of butanoic acid is present. So my initial for this first thing is 1 mole. My initial, they also said 2 moles of ethanol are mixed. So my initial for C2H5OH is 2. Do I have any products to start? 0, 0. So I have nothing to start with on the right. Now it's going to change. My amount of products is going to do what?
Go up.
My products is going to go up. What's going to happen to my reactants? Do I know by how much?
The amount your products go by.
Do I know how much? I don't know how much. So now that my products, my reactants have to go down by X. This one has to go down by X. This one has to go down by X. My products have to go up by plus X, plus x. Now, what if there would have been a coefficient of 2 on this number? Then this would have went down by a factor of 2x, right? So you have to watch out for that, but we're not worrying about that yet. So at equilibrium, for this first one, I'm going to have 1 minus x. This one, I'm going to have 2 minus x. I'm going to have x and x. So now I can write my k expression, right? So my k expression is 4, that's my k, we calculated, yes, equals x squared. You guys okay what I just did there? Product times product,
Oh, yeah.
x and x, yes? Is x squared over 1 minus x times 2 minus x. So now I've got to do some multiplying and factoring, right? So 4 equals x squared over x squared minus 3x plus 2. Agreed? I'm just doing algebra. I'm going to multiply. So when I multiply, that means 4x squared minus 12x plus 8 equals x squared. Agreed? Subtract x squared, and you end up with 3x squared minus 12x plus 8 equals 0. How am I going to solve for x?
Factor.
No. Quadratic formula.
No way we're doing a quadratic formula in science.
The only way to solve for x would be the quadratic formula. So
Very strongly.
if you were to do this, and like all of you guys have this look on your face right now, especially Maddie, all right? Like, what the beep? Like, okay, all right. I know that's what you're thinking. It's true. Is it not? Okay, it's fine. So you would plug it in the quadratic formula. It would give you a positive number, and it would give you a negative number. Can we ever have a negative concentration or a negative pressure? So then you would write down the positive number. All right? So the positive number that it would have spit out, you would have got x equals 0.845. Here's the thing. Here's the thing. You don't have to do quadratic formula. All right? So I was not trying to amp you guys up. Maddie looked like she was going to kill me. Literally. I could tell. I could tell. So I'm going to show you tomorrow why you don't have to do the quadratic formula, but we won't. You won't have to do the quadratic formula on the AP test. They won't make you do it. All right? But I just wanted to show you what you would have to do. All right? We're not even going to work through that because who wants to do that? Maddie doesn't. Okay. So now we're not done. We haven't answered the question yet. X is 0.845. They asked me the number of moles at equilibrium. So my number of moles of water at equilibrium is going to be what? 0.845. My number of moles of my ethyl butanoate is going to be what? 0.845. 0.845 moles. My number of moles of ethanol is going to be what? 2 minus 0.845, which is 1.155 moles. So this is my actual answer. And then my number of moles of ethyl butanoate is going to be 0.155, right? 0.155 moles. So, like I said, you won't have to do quadratic formula, but that's what you would have had to do. So, what did second period tell you? Did they tell you anything?
He said
Quadratic formula.
Be learning the quadratic formula.
Okay. They're mean. They're mean.
Really are.
So, flip the page. Flip the page. All right, another example. So another ester, ethyl ethanoate. Fun names. So that is EE. Can be formed by the reaction of ethene. So this is ethene. with ethanoic acid. So that's EA. In one experiment, 0.5 moles of ethene were allowed to react with 0.250 moles of ethanoic acid, and the total volume of the mixture is 500 milliliters with an inert solvent. When equilibrium has been established, the mixture was found to contain 0.220 moles of ester. Calculate the molar concentration of all three substances present at equilibrium, hence the value of Kc. Step 1 is write the reaction. So we're going to rewrite our reaction. So I'm going to have C2H4 plus CH3COOH is in equilibrium with CH3, CO2, C2H5. We are now ready to ice it. Ready to ice it.
What are the letters under the, like the abbreviation?
I'm just saying that I just read like that's ethene. This was my my ethanoic acid, and this was my ethyl ethanoate. I was just abbreviating, so I'm keeping track. So, what am I going to write down for my initial concentration of C2H4? No.
1 molar.
What?
Is it 1?
It's 1 molar. Why, Brock?
Because it's asking for the molar concentration.
It's asking for the concentration. Well done, Brock. Because I have, all right, because I have 0.5 moles, and how many liters do I have?
500 milliliters.
How many liters do I have? 0.5 liters. 0.5 divided by 0.5 is 1 molar. Usually you don't just deal in moles. Usually it's in concentration. So now there's an extra step here. So, did you like, that was nice.
Yes.
Well done. Well done. What about CH3COH? How many molar do I have of that? 0.5 molar, because I've got 0.25 divided by 0.5. So that is 0.5 molar. Do I have any product to start with? 0. Change is
Negative X.
minus x, minus x, plus x. At equilibrium, I have 1 minus x, 0.5 minus x, and x. So you can already tell this is going to be a lot nicer to solve. So, next step, write my Kc. So Kc is equal to concentration of CH3, CO2, C2H5. That's my product. Divided by the product of concentration of C2H4 times concentration of CH3COOH. Do I have any other information here? Did they give me any other information? When equilibrium had been established, the mixture was found to contain 0.220 moles of the ester, right? This is my ester. So at equilibrium, I know what X is, right? They told me that I had 0.220 moles. What's my liters? Still 0.5 liters. So I know what X is. So solve that. And what is X? So they told me the equilibrium concentration of the ester. What do you guys get for that? X is 0.44 molar. Can I solve for my other concentrations now? Yes. 0.5 minus 0.44 is 0.06 molar. 1 minus 0.44 is 0.56 molar. Now, these things are going to get substituted into my K expression. So, Kc equals 0.44 molar divided by 0.56 molar times 0.06 molar. Solve for K. What do you get? Anybody?
13.1.
I had 13.1. Are there units? No. So that's a nice intro